and impurities being throwing something else in the mix. We're also going to spend some time on element questions and letting you work on those a little bit together. So, you predict and look at pictures like on the practice test. So, these are polystyrene beads. Remember, we practice making structures using cheese balls and marbles. Polystyrene beads, exactly the same thing, except for little, right? So this is one layer, and so you can't see, kind of 3 layers to decide whether it's hexagonal close packed or cubic close packed. But we're going to come back to this picture a couple of times today to look for those impurities. So if we're looking at imperfections or defects, there's a couple of choices. We can have valencies or vacancies, vacancies, interstitials, shoving something into the sites that are there, substitutional, switching something out. All of those are point defects. There's something wrong at one point in the crystal. And maybe 2 atoms, but it's 1 point that's wrong. Then there are dislocations where there's a set of line defects. So somehow it shifts the line. And then there are grain boundaries, which are kind of 2-dimensional area defects. There is actually 3-dimensional defects as well, but we are not going to try and visualize those. So, point defects. The first one is a vacancy. Something's missing. So we've got our nice spot. We have one missing. Notice that everything, all the atoms around it are going to move a little bit because they're not shoved. This one's not shoved all the way up to touch the other one. So it's going to kind of be out of place all around there. So we're going to have some distortions within the planes. But the problem is that there's one atom missing. Then interstitials, and they're calling these self-interstitials because these are all the same atoms. So we're going to have interstitials that are different atoms, but if it's just the same atom, then you have an extra atom shoved into the lattice, and it's going to expand around it. Those are less common because it likes to eject things out of the way as it's crystallizing. It doesn't matter if there's a space that didn't get filled. So what do you see? Vacancies. I see some vacancies. Those are little dots. There's also an interstitial. See how they're not close packed right around there? That's because this interstitial got shoved in. Okay. So we've got it moving a little bit. Because we shouldn't have these little gaps right here. So sometimes it's easier to see interstitials by looking for irregular gaps around them that are not as big as a vacancy. So that's if you have atoms. So we're mostly talking about metals if we're talking about atoms, because covalent structures when we're talking about bonding. So these are ionic structures. You have ions. There are 2 different kinds of point defects that you can have, all without adding any impurities. So this is just missing something. Okay. The first one is a Schottky defect, where you have an anion and a cation that are missing. Anion and cation vacancy. Whenever we're looking at ionic structures, the defects have to add up so that the charges stay the same. So if you get rid of a cation, you have to get rid of an anion. So here's the missing cation and anion. Anion and cation, excuse me. Then the Frankel defect, named after those who described it in the papers. We just have something in the wrong place. Okay? So we have our little cation that should be right here, it's over there. It's filling maybe an octahedral hole over here, maybe a tetrahedral hole. We can't really tell, but it's in the wrong place. It should have been right there. So frequently found. So you need those two terms. Now if we start talking about adding something in, not just rearranging what we have, those are impurities. So if we're talking about impurities in metals, then we're talking about alloys, because we're adding two different metals. Sometimes we do this on purpose to increase strength, change hardness, all kinds of things. Right? You don't have pure gold in a ring if you're actually going to wear it, because it would be deformed instantly. You use an alloy instead, so that the gold has some hardness to it. Carats. So if we look at alloys, they're solutions of A and B, where those are two different metals. B is the one we have less of. And so here, it's our little B is the orange B1s. And they're kind of just taking up different sites. But they took up sites that would have been occupied by A. You've substituted B for A. So it's a substitutional alloy. So when is a substitutional alloy going to be made? When they're about the same size, so plus or minus 15% in the atomic radii. When they like to adopt the same crystal structure, so if it likes to adopt a body-centered cubic, so should the other metal that it's dissolving into. The electronegativity difference should be small, and the valences should be the same. So again, that goes back to atomic size. Less common are interstitial alloys, where we put something small into the holes of an alloy. So we've got these little teeny dots in this one. Little teeny dots, carbon inside iron. Carbonized steel makes a really strong iron. So that interstitial, they're just kind of hiding in there. They didn't replace any of the iron. So atomic size, they're going to have to be small enough to fit into the hole. Tetrahedral hole, octahedral hole, doesn't matter, but it has to fit inside the hole that is created by the close-packed alloy structure. Questions on that one? What happens if it's in between fitting in a hole and being about the same size? 6.8. Not going to fit in a hole. 0.8 of the radius. Yeah, it's not going to actually make an alloy. They're going to segregate. So we'll have, the metal 1A crystallizing over here, the metal B crystallizing over here. They don't actually mix to make a solid alloy. Another way that we can think of these is that if you're trying to dissolve up different solutions of A and B, it doesn't always have to crystallize in the same way. And so maybe you get a cubic close packed here and a hexagonal close packed over here. So you can have little sections that are in different crystal lattices. And that can happen with alloys as well. Usually that's undesirable because it makes the materials properties change as we change the crystal structure. Okay? So we don't want phase separation, which is what this is. So that's why solubility is so important. Okay, so if we go to ionic compounds, we're going to look at sodium chloride. Sodium being the little guy, chlorine being the big guy. So we can know that this is going to make a cubic chloride structure. We can draw the crystal lattice. So this is kind of front face, a little bit of the crystal structure. We can have a substitutional effect, but we have to make sure we keep the charge balance. So we can change out the sodiums for potassium, no problem. Or we can change out 2 of the sodiums for 1 calcium. And since calcium's a little bit bigger, but now more charged, they're about the same size in radii. So that's a very common substitution, right? Because we've gone down 1 row for calcium, but a +2 charge is going to be smaller. So what that means is you'd have calcium over here, and there'd be a vacancy here because we've kept the charge neutral. So that's a substitutional cation impurity. You can have anions change as well, and you can have oxygen mess up your sodium chloride, and then we would have the oxygen fit here, and you'd have a big hole here. Now, it looks like these would stay completely the same lattice, but just like our vacancies, they're going to kind of deform it just right around that space a little bit. Now, if we go into thinking not just point problems, not just little point defects or small defects in one spot, you can have larger defects over the entire crystal. And we can have line defects. And that's where if you have a crystal plane, it suddenly starts moving. Okay? So, you know, graphite shears and you make little layers of graphite. This is what's happening, but it's only sliding a half of a crystal structure. Right? So you're going to have a line, and it'll just slip where it's halfway over on the crystal lattice, and halfway over, and halfway over. So it doesn't line up perfectly in the 2 dimensions. Oops. Okay. So here, they're lining up nicely, and then something happens. This is the point where we have the line defect. This line should match up with that one, but it actually shifts over a little bit. And so then they don't line up, and you have an extra kind of row in the top half that you can have in the bottom half. So that's the edge or line dislocation is happening right here. And if you put in this extra line, that means that all the other lines have to kind of bend out. So you're going to get kind of expansion there. Too fast. Yeah, trying to see all these 3D structures, you start to think that you're actually doing it. So, now if we take a cubic structure, lots of little cubes here. What we're doing, this is a screw plane dislocation. You're turning the top half a little bit. Okay? And so that makes this gap kind of grow. And that means that where this shoved in, there's an extra thing sticking out over there. So again, this is a line dislocation. Before we had it kind of shift and add an extra line. Here it's twisting. You can twist or you can shift, either way, but it's a 1D change. And we could draw a vertices that we switched along, a line we would turn it along. So what that looks like if we flatten it out is that they're just all angled slightly. So these are things that are changed. So when we start to get into 2D or area defects, then we're looking for grain boundaries. Those are the most important thing. There's the boundaries before. Yeah. The boundaries between crystal structures. And so that's why they're called grain boundaries. Usually these are produced by how the solid is formed. Basically, one crystal was growing and it ran into another crystal that had been growing. Remember seeing when we precipitated the Prussian blue? You could see those crystals grow and run into each other. Well, that's going to produce a grain boundary if we zoom in close enough, because they grew at different rates in different organizations. And so if you look at this top section, you can see a row of atoms that's with that blue line. Okay? And then if you look at this middle section, if you draw a line on the row of atoms, it's right here. So these lines are not in the same direction. So there's a difference there where the crystals grew differently, and so that is the grain boundary. So if we remove that, there's this rough edges here. Okay, we could draw lots of lines that are parallel to that blue line above it, and lots of lines that are parallel to this blue line. But they're always going to have that curve where those two blue lines do not meet. Down here, same kind of thing. If we draw our blue line, it goes this way. 135 degrees or so from the other one, and so that's going to produce another grain boundary. So, the good thing about this is it will make it so that it's less likely to slip and make a line defect and a line problem, so you're less likely to have shearing. So in some ways it makes it stronger because you can't have that shearing, the dislocation motion. But the irregularities are going to be where chemical reactions occur, because they're less coordinated, there's ability to get other atoms in here, so grain boundaries are where the chemistry usually happens. Whether that be good chemistry or rusting of metals, that can be good or bad. Okay, so what do you see?
Everything.
Grain boundaries. Lots of grain boundaries. Let me point out one. This line right here is a grain boundary. There's then this one, and that one, and this one. You can probably see more. There's one up here. Okay. See another one right over here. Okay, so you could start marking it all up. Okay, so if we're looking at defects, point, line, and area defects are always there in solids. Depending on how much energy you're putting into the system, the more energy you have, the more likely you are to make defects, because things can move around. So you can control how many vacancies by controlling the temperature. So that actually has a big part of how we make materials for things. So a slow heating, slow cooling process, so we can make very even structures, very even alloys, is really important. So you can't mess with steel processing a lot if you want to get steel that's going to actually make a building, because you don't want to have vacancies, you don't want to have impurities that you didn't intend. Buildings falling down, not a good thing. So we can control grain boundaries that help with crystal slip, or that make it so that they're slipping apart easy if we have lots of line defects. And remember, defects, although you think of defects as bad, they may not be a bad thing. Right? Making an alloy can make it stronger. Making a grain boundary could make it so it doesn't slip. So it also could go that way where it makes a horrible material. Okay? So it can be good or bad. Plastic deformation, whether it can return to the same structure or not. That's what plastic deformation is. So questions on those defects? So, I think you had a picture that looked like that and said, label things.
Yes.
Okay? If we had a picture that had both cations and anions, we would be able to label more things. What other things, like this assumes that it's all one solid, right? So it assumes that it's a metal or an alloy. If we started coloring in those dots, making them cations and anions, what are the different things that we could label? The what?
The substitutional.
So you can look for a substitutional cation, where we changed out, if we had red and blue appear, oh, suddenly there's an orange thing that appeared. Is that a cation or an anion? Had to go with, if it was isoelectronic, so same electronic structure, it could directly substitute. If it was a +2, then it had to take out 2 of the sodiums, 2 of the +1s. What other things?
Schottky and Frankel.
Yeah, so you could look for the Schottky and the Frankel defects. Frankel being it's just in the wrong place. So it's there, but it's in the wrong place. Or Frankel being that both the cation and the anion are missing. Now, the cation and the anion missing don't have to be in the same place. Okay? They can be really far apart in the structure. Now, for the test, I'm going to put them on other sides of the page. Probably not, because that's just cruel. Yeah, there's one little dot that's out of place and that one little dot up there. No. But they don't have to be nearest neighbors, like we saw in that picture.
So it's not always obvious.
No, it's not always obvious. Just like in some of these, do you label this a vacancies, or do you label it an interstitial, or is it just part of the grain boundary? That's a little hard to tell. Okay? It happens that when I counted them, it looks like an interstitial, and it is along the grain boundary, so that's why I labeled it that way. A little more obvious to see some of the other ones. Do I expect if we have a labeling picture that you get everything that's wrong with the picture? No. You need to label a vacancy, a grain boundary. Okay, so in looking at the lovely questions that you came up for one another, some of these are hard. And I thought, I think we better work on them together. So I want you to get in groups of 4 and come up with answers. I'm going to post it. If there are questions that just don't make sense, we're going to number these and just cross them out. Because there are some that either through translation or through poor handwriting didn't actually make it into real questions. This is just what Shelby could read. Some of them don't make sense. Okay, so get in groups of 4. If you have your questions, great. If we need to, hopefully in groups of 4, at least one person will have questions. If not, I'll make copies.
Include all my answers. I did wonderful. Okay. Should I go on the other side?
That will definitely work.
I don't know. I only have this one.
You guys have a set of questions you approve.
I don't have them, but I could bring them with.
No questions?
No.
Okay. You can get it back.
I can. That's
So why don't you guys get it back?